Let's take a look. So this is the answer to question number 2 in the circular motion platform challenge. Now the first thing that we need to say from the start of this solution is that right here, object A, as it goes around in a circle, it's moving at that maximum speed that we have just discovered. So that's what we say in the beginning here. This object, if it is at location, a distance capital R away from the center, its tangential speed is that square root mu s g r. Okay, that's step 1. All right. Now to build the solution up, I want to ask you a few questions. Question, I guess part A to build this up. If the block at A is moving that fast that we just talked about right now, is block B moving faster, slower, or the same tangential speed? So I'll write that out here. Is B moving slower, faster, or same tangential speed? Assuming that it's going in a circle. All right, give that a shot, pause the video, and think about it for a second. So this is a good test of understanding to see if you recall that the tangential speed of an object going around in a circle at a constant speed is 2 pi r divided by the period. Now this is the time to go around once, the period, and it's going to take exactly the same amount of time for A and B to go around in a circle, assuming that they both do, right? So therefore, you can clearly see, if that's the case, that the tangential velocity is directly proportional to the radius. Therefore, if we go from r to 2 times as much a distance away, and we're moving in a circle, that would require twice as much tangential speed. So therefore, it is, and let's write this down as a fact, it is a fact that if B is going in a circle at constant speed, it must be traveling twice as fast, or moving twice as fast as A. Okay, that's just a mathematical, pretty much geometric fact that that has to be true. All right, now what we can do is solve for the maximum speed that B must have, and then compare the two. So that's what we'll do now. So part B, determine V max at location B. So if you haven't done that, pause the video and try to do it. And the subtlety here is just doing everything kind of in the same variable so you can actually compare the two solutions. All right, so give it a shot and see if you can do it. All right, so I've just written down Newton's second law. It's the same physics. You have a net inward force coming from the static force of friction. That equals mv squared over r, but I've put r sub b because now we're talking about object B. So we'll plug in. We know our maximum static friction force is mu s mg, and that's going to equal m, and then we'll put v max, and I guess I'll put a b down here because it's the maximum speed for for B, and then we'll square that, and then divide by, well, what is RB? We're parameterizing things in terms of this capital R, which represents just the distance from the center to location A. So we know that B is twice as far away, so we can do 2 times capital R, and that would give us an ability to compare these two in similar variables. So we'll plug that in to R. That's how far away it is. All right, so we'll go ahead and cancel out the m's again. Great. Solve for this with the math and see what happens. So do that, and you're going to get that the maximum speed at B is going to equal the square root of, well, there's going to be a 2 under here now. We're going to get mu s g and then capital R. Now we can write that in a slightly different way. I'll bring out root 2 in front, and then I'll multiply that by root mu s g r. Now why did I do that? Why did I write it like this? So you can pause the video and figure it out, and maybe Now you might be able to piece together the solution if you weren't able to get to this part. So pause the video, give some more thought to this, and see if you can finally figure out the answer to the question if B would slip or not, and then we'll take a look. All right, so you can see up here, up in the top part of the video, I've outlined a few things. I rewrote the maximum speed that is that you can have at location A, so mu s g capital R. And then because we're writing everything in the same variables, that's why we had capital R here and then 2 times capital R there. That allows us to compare things. We can write that the maximum speed at B is root 2 times this other parameter, which is equal to the maximum speed at A. So we get 1.41 times square root mu s g R. And if you just look above, right, this thing under the radical is identical to this. And so the maximum speed at B is then 1.41 times the maximum speed at A. So like, what does that really mean? It means that if we take the object and move it to location B, the fastest it would be able to go compared to its speed at A would be 1.41 times. Now think about that for a second, right? If it goes any faster than that, it's going to slip. So friction is, kind of providing this constraint that will only allow us to go 1.41 times as fast as we were going here if we still want to move in a circle without slipping, right? So then how can you connect what's over on the left-hand side to the fact on the right-hand side? This is the final piece of the logical puzzle, right? So maybe take a second, if you're not seeing it right now, pause the video and think there's some things on the left-hand side of the screen that you're seeing, the math, and then there's a fact on the right-hand side. And you want to bring the two together to try to then articulate the final answer to this question, if block B would slip if placed there. All right, give it a shot and we'll see. All right, well, let's review this fact. It's important to write those down, which is why we did that, because it's a logical principle that you've already determined in your past analysis that has to be true. And then you can use that effectively to figure out what's going to happen in certain changes in the system like we're doing here. So if B is going in a circle at constant speed, which we want it to do if it does not slip, right? So if B gets there and it's perfectly okay going around in a circle, it will for sure be traveling at exactly twice the speed as object A. Okay, so that's a fact. Then we come over here. The physics of circular motion and friction combined together, though, tell us that B can only travel 1.41 times as fast as A. And if it goes any faster than that, it's going to slip off. So therefore, we can never get up to going twice as fast in this physical scenario. It's not possible because of the way friction is working. It has to be true over here to go in a circle. But the physics of friction and how it's combining with circular motion is absolutely not allowing us to get up to twice as fast. It's only allowing us to get up to 1.41 times as fast as A. And so therefore, when we get there, when we go to location B, we're going to slip off because location B can only support 1.41 times the speed of A, not twice the speed of A. Great. So that's the solution. Now there's one more way that you could kind of analyze this. And I'd like to look at that next. So I'm going to ask you one more kind of follow-up question to probe your understanding of this unit. So let's see that now. Now another way you can think about this problem is just by thinking about forces, specifically centripetal forces. And what I've done over here is I've drawn a vector on object A. At this location, at this moment in time, you're seeing the centripetal force on A, which is, remember, coming from the force of friction. So that's the size of the centripetal force at A. My question is, if it was true that B was going in a circle and it was not slipping, of course there would need to be a centripetal force for that to occur. And the question is, would that centripetal force that B experiences be smaller, the same size, or larger. I've kind of drawn 3 arrows over here. So do you think the centripetal force that B would require would be smaller, about the same size as A, or would it need to be larger? And then bonus points, by what factor would it be different if you think it's different? Would it be 4 times as much, 2 times as much, 3 times as much, maybe a half as much, 1/3 as much, or maybe it's just the same? Okay, give it a shot, work it out, and then we'll come at the same question with a force analysis. All right, well, if you think about some velocity vectors at location A, you can see them here. So here's the object at location A right here. It's going tangentially this way, but then a little bit later in time, it's going to be going kind of at an angle like that. I'm going to go, and the velocity vector is just going to rotate around. That's what these vectors are over here, velocity vectors. Let me just write this actually. So this would be like V initial and then V final, for example, for A, and then same thing for B, V initial and then V final, and then VI, and then V final here, and then same thing here, VI and V final. And so what I've tried to show is that the change in the velocity vector is larger for B. And you can see that here. We're just doing vector subtraction to find the change in the velocity vector. We've seen that before. And you can see how, because object B has, or when the object is at location B, it has larger velocity vectors because you're going faster out there just because of the geometry of a circle. Remember, twice as fast. These vectors are twice as large. And so you can see it would require more change in velocity. Well, why is that important, right? Well, remember, acceleration is the change in velocity over the change in time. And they're both going to take the same amount of time. To, translate and rotate around. Because they're connected to the same platform, right? So the time's the same. Therefore, B would require a larger acceleration. You can see that right here, just because this is a larger value for the change in velocity vector. Why is that important? Well, because we know that F is equal to ma, right? So centripetal force is going to equal mass times the centripetal acceleration. So now we've just shown that we know acceleration is going to be larger. In fact, how much larger? Twice as large. And so the centripetal force is going to need to be twice as large as well. That's an argument just building it up from the velocity vectors. Now another way you can do the same argument is just to use the second law. So let's do that over here. And this is a case where we know that the centripetal force is going to be equal to mv squared over r. And then it's the same mass, so that's a constant. So the centripetal force is directly proportional to this ratio. Square the speed and then divide by the radius. So we can do some factor analysis here. We'll write it up top here. We could say as we go from A to B, we can see that we double our radius and then we also double our speed. We've talked about that before. So 2 things are doubling at once. So to do your factor analysis, you double the first thing, but you have to square it for proportional reasoning. And then you double the thing on the bottom and you get 4 over 2. And so the centripetal force doubles. It becomes twice as large. So therefore, this means that we would expect to find a centripetal force vector that's double. So B requires exactly twice as much centripetal force. To move in a circle. On the platform. So that's a fact. Now, finally, can we get that centripetal force? Where can we get it from? The only place to get it from is from friction, right? So you look at that physics, and we're reminded that we've got, let's just draw this up here. It's getting a little messy, but we've got a gravitational force pulling down, a normal force pushing up, and then we had that friction force here, that static friction force, right? But the issue is that the static friction force max, what was it? Well, it's mu mg. Did we change anything about the coefficient? No. Did we change the field strength? No. Did we change the mass of the object? No. We didn't do anything at all to increase the maximum static friction force. In fact, we made the claim, or the assumption, I guess, or I guess the initial condition would be the better way to state that, is that we used the maximum amount of friction force that we had available at location A. So we came along and assumed when the object is at A going around in the smaller circle, we're going to use all of the maximum static friction force that we had. Now, that was required in order to make the condition so we could solve for the maximum speed that it would go around. Because if you try to spin it any faster, friction cannot further increase its inward force to still allow you to be moving in that circle. And so we've already set the maximum static friction force at this value. Right, so there's no more to give. So if we take the block at that speed and place it here, we'll place it there. Friction will try to do its thing for sure. It will say, all right, I'm going to give you the maximum static friction force I can, and it's equal to however many newtons, just like we had at spot A. But that's not going to be enough for you to be moving in a circle here. And so you're going to slip, and then you're going to start sliding across the surface. And now we're no longer in static land. We're in totally different problem, kinetic friction, where the thing's sliding across a rotating platform with friction, and that's a pretty complicated problem that we're not going to look at. All right, so the bottom line, I guess, is that as we go from A to B, we just cannot increase our centripetal force at all because of the static friction force being exactly the same value. There's no way to get more static friction force than what we had here at point A if we're going at that maximum speed at point A right there. Now, you could actually, if you had some other ability in this problem to provide more force inwards, like let's say you had a rocket. I always like to use that example. Like let's say you had like a rocket thruster coming out like this. Okay, so you bring this thing over here, and then you get half the force you need from static friction, and then maybe the other half comes from that rocket thruster, which also points inwards. Well, now you can do it. Now you can be moving in the circle out there because you're able to get up to twice as fast as you were moving at point A, because you have this, additional inward force to help you get more acceleration, which again is required for you to change your velocity vectors in the same amount of time. So it all kind of pieces together. All right, so there's a lot to this. As you can see, there's different ways of thinking about it and building up your understanding. And hopefully you can follow all of them. You might have to pause the video and kind of just rework this. But this is a really cool challenge problem to think about what happens with friction on a moving platform at different locations and kind of like all the subtleties that are there. All right, so I'll end the video there. Hopefully you got something out of that, and we'll see you later in future challenges.